Just hash. Yeah, sure. Start recording. I can actually change this like this. You can have a seat. So is it audible to the Zoom folks? I see a chat. Okay.
Yep.
So cool. So hey guys, welcome to Recitation 5 and welcome to the first recitation which is in person. So that's actually a milestone for us. So thanks to everyone who has come here and thanks for the people in Zoom who have joined. So we'll be going over 2D convolutional networks. As you all know, yesterday we released the homework part 1. So going over this recitation and next week's slides of Professor Bhiksha would be helpful for you to like start and complete the homeworks. So let's get started. Okay. So first, before going into what convolutional neural networks is, let us get to know what an image is. So as you can see, image is basically a function of intensity. So the function depends on the location or the pixel coordinate. So as you can see from the image, in the right hand side, you see a matrix, a big matrix. So each position of the matrix is indexed by x and y, and each x and y coordinate has a particular intensity value. So you can consider this matrix to be a function of intensity values. So as you can see from this image, even though it's kind of pixelated, you can see various numbers. So each, for example, the first 0 cross 0, this position has an intensity of 150 or something. So that's how an image is formed. It's basically a 2D function of various intensity, and changes in these intensities is what gives you features of the image like edges and so on. So this is actually for a very low resolution image, but the same actually applies to a high resolution image as well. And another thing to notice is that this is a single channel image. Single channel in the sense that it just has two dimensions, that is x and y. So these types of images are also called as grayscale images. And going on to the next, there's actually a multi-channel image. So whatever we see in our phones, everything are multi-channel images. So they are colored, right? So they have three channels: the red channel, green channel, and blue channel. So they are just concatenation of many grayscale channels together. So each is kind of a grayscale channels, a single channel. You just need to concatenate everything to get a color image. And there are many representation of RGB images. 3 cross M cross N is kind of how PyTorch sees it, and M cross N cross C is how like other computer vision CV2 libraries see it. So you just need to concatenate many single channel images together to get a multi-channel image. So is everyone kind of okay with what an image is and multi-channel images? Okay, thanks. Zoom, I think it's clear. Okay, so going on to what CNN does, which is kind of a little different than MLP. So you guys must have known about scanning MLPs, right? Like from Thursday's lecture and Tuesday's lecture. Take a regular MLP, for instance. It takes a feature vector as an input, does some sort of a processing, and gives you a feature vector as the output. So CNN, what it does is, it takes a feature map. As you can see, it is two-dimensional. This is a one-channel input, but two-dimensional. Takes a feature map, we call it a feature map, and gives a feature map as the output. So that's kind of the basic thing which CNN does, and we'll look into what this black box is. So we'll go on to the components of a convolutional neural networks. As you all know, every neural network consists of an input, weight, and in CNN's bias can be optional, but we'll just include it for intuition purpose and like for understanding. So consider this. This is an image, an input image of size 4 cross 4. And as you can see, it is indexed by 1, 1, 1, 1, 2, or 0, 0 for in Python. And the kernel is basically a filter, which is a 4 cross 4 filter. So kernel is basically the weight of a convolutional neural network, such as you will have the regular weights in an MLP. So if you actually remember from Professor Biksha's lecture on scanning MLP, you would have noticed that an MLP is used for scanning each and every patches of the input. So basically, in CNNs, this filter will be scanning each and every patches of the input. So that's the big difference, big but a little small difference in CNNs. So let us see how this actually happens. So this is the operation which CNNs do. So A is convolved with W, and we actually add a bias to get an affine transformation. So, but how is this done? What exactly is this operate? So yeah, signal processing folks might know that convolution is an element-wise product and a summation. So we'll apply the same concept to this. So as you can see, this is the filter, and the filter is used to convolve on the input image. So as you can see, this filter is 2 cross 2, and you keep the filter on a 2 cross 2 patch of the image, the first patch of the image, and you do an element-wise product and summation. So as you can see, Z prime 1 1 is basically x1. Wait, I'll actually use this so Zoom people can see. Z prime 1 1 is basically x11 into w11, x12 into w12, x21 into w121, x22 into w22. So you have to take the element-wise product and do a summation. That's what convolution does in a single step. So doing this, you get the first element of your output map. So the next step, the filters passes a pixel and does the same operation again to produce the second element of the output feature map. So this process continues until the whole output map is formed. So, and one thing to note is that if you can go back, yeah, as you can see, the filter while going from one step to another, it just passes one pixel. So in this convolution, the step size or the stride is basically 1 because it passes 1 pixel. And after convolving with the filter, you just add the bias to every element of the output. So this B1 is added to each and every element of the output to produce the final output map. This is the intermediate output, and you just add the bias to all the elements to get the output map. So, okay. Does anyone have any doubts in CN? Yeah. B1. B1 is a scalar. Scalar. Yeah. So yeah, I'll come to that. This is a one-channel convolution. So you have one channel input. You convolve with a single channel filter. You get a single channel output. So for one particular channel, you have a single number as a scale as a bias. So if you have multiple output channels, you have multiple biases. So we'll go on to that in the upcoming slides. Okay. So as you can see from the previous diagrams, like you have a 4 cross 4 image, but after convolving, it has reduced the size to like 3 cross 3. So can anyone guess why this is happening? Yeah. Yeah, that's correct. So basically, because of the boundaries, the kernel cannot convolve in the boundaries of the image. So that's why the maximum number of steps which this filter can actually take is 3, not 4. If it takes 4 steps, you can get a 4 element output. So that's why. So because of the boundaries of the image, and because of this, you actually get a formula such as the output size is input size minus kernel size divided by stride plus 1. It's kind of intuitive, this formula, how actually comes. And we can actually consider this example. Now you have an input of size 4 cross 4. You have a kernel of size 3 cross 3. Convolving this, you get an output of size 2 cross 2. Can anyone? Okay, actually she told the answer. I thought of asking this as a question. So how would you actually preserve this input size to the output? You just need to pad the input with zeros. So if you pad it and then convolve it, you don't actually lose the size of the input. A 4 cross 4 image produces a 4 cross 4 output. So that's basically how it's done to like conserve your input shape. Okay, now let us go on to slide 2. Is anyone having any doubts until now? Okay, Zoom, there are a lot of chats. Okay, cool. Just answer Zoom if possible. Yeah, okay. So moving on to stride 2 convolutions. As told earlier, this is just an intuitive example of how stride 2 is done. So this is actually an example from the homework write-up. So this is an input image of size 5 cross 5. This is a kernel of size 3 cross 3 with the bias 1 cross 1. Bias is for one channel output. That's why we have a single number as a bias. Okay, moving on to the steps followed. Yeah. Okay. So as you can see, the first step is to place filter on this, the first patch of the image, the first 3 cross 3 patch of the image. Do an element-wise multiplication and you get 10 as the output. And since the stride is 2, the filter crosses 2 pixels and goes to the next image patch as so. So it's kind of intuitive that the filter passes 2 steps, 2 pixels to get the next output. You do the same operation of taking an element-wise multiplication and a summation to get this output. And since stride is 2, you have to pass 2 pixels in both the x direction and the y direction. So that's why we have actually come 2 pixels down for the next patch. This gives you the output -6, and the final one gives you -9. Add bias to this, you get this as the output map. And yeah, so this is something which we have introduced a little new in this homework. So how will you kind of interpret stride greater than 1 convolutions? So as you can see, taking this as the input, this image as the input, convolving with this filter and with this adding this bias to it, the stride 1 output is this left output map. The stride 2 output is the right output map. So can anyone take a guess on how this output, the stride 1 output and stride 2 output are related?
Downsampling?
Taking a max pooling of like
Yeah,
2
downsampling. It's not dropping the elements. So yeah, so both are correct. So you just drop the intermediate elements. That's how you can actually derive your stride 2 output from stride 1. So it's kind of intuitive if you think stride 2 as a combination of stride 1 output and downsampling or dropping some intermediate elements. And yeah, going on to multi-channel convolutions. The previous examples were for single channel input and single channel filters. So if you have a multi-channel image such as RGB image, you would need a single channel kernel to convolve with each and every channel of the input image. So you will have 3 filter channels per filter, because if you take an RGB image, you have 3 channels. And as you know, each channel, convolving each filter channel with the input channel, you get a single output map. So for 3 input channels, you get 3 output maps. But to incorporate depth information, you just add all the channels together. So that's how multi-channel convolutions are done. So as you can see from the image, you have an input which is 3 channel. The kernel is 3 channel. Convolving the first channel of the filter with the first channel of the input, you get the first output map, and so on for the rest too. But incorporating depth information together, you just add all these channels together element wise to get the final output map. So this is kind of observable that one filter produces one output map. If you use like n filters, you get n output maps, and n output maps will be like concatenated at the output. So is it clear to everyone about multi-channel filtering, multi-channel convolution? Yeah. Yeah, no issues. Yeah. What?
Why is it necessary to add all the maps at the end?
You need to incorporate. If you actually take this channel, right, and convolve it with the input, You just get the spatial features of the first channel. You don't have any relationship between the depth-wise information. So you try to like squeeze all the information together as one channel. Yeah. Every information. Yeah. One filter to capture like a couple of features of every channel, the whole image. No, that's not very related. You don't actually have to relate those two. Changing the slide is depending upon the application. If you want to reduce the input output map size, you can actually convolve with the slide. So that's it, nothing else. So cool. Moving on to an example of multi-channel convolution. You have input which has two channels, and the weights, you have three kernels. Since input has two channels, each kernel has two channels. And you can take like any number of filters based upon your application. In this example, we have three filters. Three filters will produce three output channels. So that's why we have a bias of shape 3 cross 1, each and every element corresponding to one output channel. I hope that's clear. So doing the steps again, as you can see, the first channel of this is convolution with the first filter. The first channel, that is the light pink one, is actually convolving the first channel of the input image. The second channel of the filter convolves with the second channel of the input image. Do an element-wise multiplication and addition. Add both the outputs together, you get 10. So this is done for all other steps. We have actually taken the example of side convolution because side convolution takes up a lot of space computationally and also in the slide. So that's right. Okay, this is for the second filter, you get a different output map. For the third filter, you get a different output map. The final thing is to just concatenate all the output maps together. So that's it. So this output map is of the shape. 2 is how you calculate with that formula. 3 is the number of filters. 3 filters gives you 3 output maps. So it's simple. Okay, moving on to pooling. Pooling is usually done. Yeah.
So when you said adding the map, so you did not add them up. You just want to concatenate all the data.
Yeah, the final one, this is concatenation.
Yeah, so you didn't need to add the layers together.
For a single filter, you kind of need to add all the output responses. For a single filter, it should produce one output map. So that's right. For the final one, you have like n filters, n output maps, you concatenate together. That's it.
So for just one of the kernels, like for example, you have like this one ends up being 12, -4, 6, 5.
Yeah.
That first kernel 1.
Yeah.
So you're taking like the dark red filter and convolving that on one of the channels and the light red and convolving it on the other, and then you're adding the two.
Yeah.
The 2 by 2 together, and that was giving 12, -4, 6, 5.
Yeah. Not 2 by 2. You get from each convolution, you get 2 scalars. You just add it, and you get 10 or 6 for the first step.
Okay.
Yeah. Yeah.
So for each filter in the kernel, we play 2 by 2.
For each filter.
Yeah, for each filter in each kernel,
Hmm.
play the 2 by 2.
There's no each filter. Each filter has channels.
For kernel 1,
Yeah,
we have 2 filter blocks.
2 channels.
Yeah, 2 channels.
Hmm.
And then for each channel,
Hmm.
we create the 2 by 2 because we have like 2.
No. Slide is not kind of related to how many channels are there. It just depends on how far this filter needs to take a step during each and every convolution.
So how do we combine that for the kernel 1?
Kernel 1.
Yeah.
No, it's just arbitrary. You can even have a slide 1 with the same configuration. If you have a slide 1, you will get a bigger output map. That's it. So nothing else. So the next question, I think the lady in the back actually raised her hand. Okay, moving on to polling.
Hi,
So polling is
I had a
basically
question.
followed after convolution. Polling is done to like as a jitter variant. So
Hello.
and polling is
Hello.
that's fine.
Yeah, I had a question regarding the previous slide.
It's good, right? So it's just polling is done just for the sake of jitter variance. So there are two types of polling. One is match polling. So let us see what match polling is. Match polling is done in this example. It's done with a kernel size of 2 cross 2 and a side of 2. As you can see, the kernel is 2 cross 2. The input is 4 cross 4. Hello? Yeah, okay. I stand here. Hello? Is it audible? Hello? Hello? Yeah, okay. Okay, moving on to what polling is. As you can see, okay, this is a 4 cross 4 input image, and each colored 2 cross 2 patch shows where the 2 cross 2 filter of the match polling is placed on. So in this red patch, you see the first step taken by the match pool filter. So in the first step, the max element is 20. So max pool filter takes 20 and outputs it. And after 2 strides, it goes to the yellow patch, takes 30 because it's a max element, and that's how max polling is done. And moving on to the next type of polling. Yeah, okay. Okay, this is actually mean polling, so sorry for the typo. Mean polling is basically done by the same stride in this example. The only variation is that you just average all the elements instead of taking the maximum element. So that's how polling is done. So that's all from my side. I'll give the mic.
Question on Zoom.
Yeah.
We want to know how do you do polling when there are multiple channels?
Hmm?
How do you do polling when there are multiple channels?
Yeah, if you actually do polling separately for the different channels. So if you have n channel input, you get an n channel output. Polling just reduces the spatial dimension. It doesn't reduce the depth. It doesn't reduce the number of channels. So as you can see here, it reduces the spatial dimension, the x and y, but it does not reduce the channel. Okay. So full. I'll give the mic to Mansi.
All right. So we are going to talk about how to do back propagation in CNN. So Aparajit had explained in detail about how the forward propagation happens. We will look at how the back propagation works. So in order to do back propagation, we must have seen
Audio is very low.
audio.
Audio is low. Just speak into the mic.
Yeah, in your first assignment, also you must have seen in order to do back propagation, you needed the DLDZ, that's the loss derivative of the loss with respect to the output. So the first thing that you need is the gradient of the loss. Too bad, is it? Is it better now? I don't have it. It is still audible to you. Hello, is it better?
Hello.
Is it audible to the Zoom folks? It's good, right? All right. Okay, awesome. So, all right, I'll have to talk from here itself. I cannot move around. So in the backward pass, we will have to have the gradient of the loss with respect to the next layer. And we'll also need to calculate the local gradients, that is the gradient of loss with respect to the input of the CNN and with respect to the weights or the filters of the CNN. Yeah. So we've seen CNN with single stride. So considering this as our input map X and the filter is F as shown. And we are going to look at an example of stride equals to 1 in both the directions, X and Y direction. So that is going to produce an output map as shown here. It has 4 elements. So basically you had a 3x3 input convolving with a 2x2 filter. You get a 2x2 output. So here's that animation to look at. So you have 4 outputs, and now you want to calculate the derivative of these outputs with respect to your inputs, that is all the X's, and with respect to all the filters, that is all the F's that you see in it. So for any particular layer, like for a convolution operation, as seen here, your inputs are X and F, your output is O. So you have the derivative of loss with respect to O over here. You have to find the derivative of loss with respect to X and the derivative of loss with respect to F. So how do you do that? Any answers? You've already used it. No, actually, these two are separate inputs, so they are obviously related to each other. But what I expected was this: you'll have to use chain rule. So it's the gradient of loss with respect to the filter is what we're going to look at to begin with. Is going to be gradient of loss with respect to output multiplied by the local gradient, which is gradient of output with respect to the filter. And now you have a bunch of filter elements, you have a bunch of output elements. So say you want to find the gradient of loss with respect to a particular filter element. You are going to take gradient of loss with respect to output of a particular element, multiply that with gradient of output with respect to that particular filter element, and then you will sum over all the outputs. So we'll expand this equation here. So as you can see, the gradient of loss with respect to F11 is going to have the gradient of loss with respect to the output 1, O11, multiplied by gradient of O11 with respect to F11. So you can follow the formula from there. Going forward, we are simplifying those equations even further. So these were our forward pass equations, as you can see. And in this particular part, we had a gradient of loss with respect to O11 multiplied by gradient of O11 with respect to F11. So in order to calculate that, if you look at the forward pass equations, so gradient of O11 with respect to F11 is going to be X11. Similarly, you can look that up for all other examples as well. Yeah, go on.
Can you explain the nomenclature once?
What is 1, 1, what is 1, 2?
Okay, yeah. So yeah, this is your input map where all of your inputs are like x1, 1, 1, 2, 1, 3 in that order. And this is your filter, 2 cross 2 filter, f1, 1, 1, 2, 2, 1, 2, 2. All right. And this is how we have got all your forward path equations. It's the standard convolution that you did. This is just for single channel. So yeah.
Mansi, can you repeat the derivation part?
Yeah. So, okay. So now you have to find the gradient of loss with respect to filter. So which is all the elements in the filter. So you have to find these 4 terms essentially. That is the gradient of loss with respect to all 4 filter elements. F11, F12, F21, and F2. So that is going to be summation of the gradient of loss with respect to a particular output multiplied by gradient of output with respect to that filter input. So as you can see, gradient of loss with respect to O11 is the first term. Gradient of loss with respect to O12 is the second term. So that's like for all the outputs that you have got. So basically you have 4 outputs here, O11, 12, 21, and 22. So you would have one term corresponding to every output. So that will be multiplied with the corresponding gradient of the output with respect to F11. So these are the multiplicative terms that you have. And gradient of loss with respect to output is what we would already have from the next layer. And the ones that we want to calculate is gradient of output with respect to F11. So how would you do that? So we'll have to look at the equations that we got from the forward pass, and the math is going to follow from that. So you have to find, say, the gradient of O11 with respect to F11. What would that be? That's going to be X11, and that is exactly being plugged over here. So it's just simplification of the formula. You can just look through the slides and you should understand. Let's look at some other example. So you want to find gradient of O21 with respect to, say, F22. So that's going to be X32, and that's what you plug in over here. Going forward, so yeah, basically, if you look at this particular thing, towards your left, you have all your forward pass equations, and you see that it's like a linear combination of your inputs and the filters. If you see on the right, you still see a linear combination of your output map, which is like the gradient of loss with respect to output, and your inputs, the X. So even the gradient of loss with respect to the filter, this particular operation on the right can be viewed as a convolution. So that's what we're going to see next. So this can be viewed as a convolution between your input map and your loss gradient map that you had from the next layer. So if you just convolve these 2 things, you're going to get the gradient of loss with respect to filter. So yeah, next on, we are going to find the gradient of loss with respect to inputs. So filters is what we found now, and it's a convolution operation between your input map and the loss gradients that you get from the next layer. Now we'll see gradient of loss with respect to input. We again have the same formula. So gradient of loss, we have to find with respect to every single input. So for a particular input, it's going to be gradient of loss with respect to, say, one output multiplied by gradient of loss with respect to gradient of output with respect to that particular input. And then you will sum it over all the possible outputs. So we had these forward pass equations, and we have total of 9 inputs. So X11 through X33. So we'll have to find the gradient of loss with respect to all of these inputs. So there'll be a total of 9 equations. So we're looking at the first 3 over here, gradient of loss with respect to X11. So if you see at the equations, we have a term, here we'll have a term like gradient of loss with respect to output multiplied by gradient of O11 with respect to x11. So see the dependency between O11 and x11. You can see that there's only one term relating to it. So the derivative here is going to be f11. Next up is say gradient of loss with respect to x12. So you will have gradient of loss with respect to, you're going to consider for like x12 contributes to which outputs. So for that, if you look at the equations, x12 you can find in the equation of O12, and you can find it in the equation of O11. So x12 is contributing only to O11 and O12. That's why we just have two terms. For all the other terms, the gradient will become 0. So let's look for some other input. So say the gradient of loss with respect to x22. So which outputs are affected by x22? Can anyone tell that? Which outputs are going to be affected by the input term x22? Yes, and are there any other outputs? Yes, so I think as you can see, x22 comes in every equation, right? So all the outputs are affected by x22. That's why you see like 4 terms in here. So I have the equations for gradient of loss with respect to every input term. And in this particular situation, again, we see that it is on the right side, whatever equations we have, those are also linear combinations of your output feature maps and your and your filters. So even that can be visualized as a convolution. But in order to do that, we'll have to do some manipulation with the filter. So we'll be taking our input filter and flipping it vertically and horizontally. That's a total 180-degree flip. So this is what you get after you flip it horizontally and vertically. And then do a full convolution with your loss gradient map. So by full convolution, I mean that you're going to consider convolution with padding. So the way Aparajit had explained, that you will be padding your input map with zeros at the edges. So you will be padding with zeros, and then you'll be doing a full convolution. So yeah, this particular thing right now does not have a padding, but you can see like every single corner and edge is being covered by the output map. So what's the takeaway for stride 1 BackProp? That the gradient of loss with respect to filter can be viewed as a convolution between your input X and the gradient of loss with respect to output. Also, the gradient of loss with respect to inputs can be viewed as a convolution, but it's a full convolution with padding, with some change in the filter. That's like 180-degree rotated filter. And again, the same loss gradient on gradient of loss with respect to your outputs. So what happens when stride is greater than 1? So here's another example. This is our input activation. A slight change in notations. It's starting from 0 now. So it goes to x00 to x44. This is a 5x5 input map. We have a 3x3 filter, and that's going to produce a 2x2 output map if we use a stride of 2, right? So this is how the convolution can be viewed for stride equals to 2. So it's going to skip 2 pixels and go to the next one. So these are the forward pass equations, and I think these are easy to follow. Now we need to see how do you find gradient of loss with respect to filter. So again, we have the gradient of loss with respect to outputs. Slight change in notation again. O was used in the previous example. Here it's Y. So Y are your outputs. So we have the gradient of loss with respect to outputs, and from there we have to find the gradient of loss with respect to filters. It's the same equation again that we had seen earlier. Now let's have a look how does this actually scale to the equations. So let's say, for example, we want to find gradient of loss with respect to F00. So in order to do that, we need to see which outputs are affected by F00. So these are the equations that we have. So you see that all the 4 outputs are going to be affected by F00. So there are going to be 4 terms in your gradient equation. So that's gradient of loss with respect to F00 will have all the 4 terms. Similarly, if you say you want to find gradient of loss with respect to F01, again, F01 contributes to all the 4 outputs, and that's why you have 4 terms here as well. These are some of the examples. Now let's see if we can find a pattern in it so that you can view it as a convolution. So if you see F22 is multiplied with what terms in here. So this is like finding gradient of loss with respect to F22. So you have these terms X22, X24, X42, and X44. So basically these terms X22, X24, X42, and X44 are contributing to it. So this plus in the middle actually is, I mean, these inputs are sort of not contributing. So what we can do in order to view this as a convolution is we can dilate or upsample our output gradient map with zeros. So we are dilating it with stride -1. So our stride was 2, so 2 minus 1. So 1 zeros are going to come. So 1 row of zeros and 1 column of zeros are going to come in. So first thing that we do is we upsample our output gradient map and then convolve our output gradient map with the inputs. So again, we are viewing this as a convolution of the input and the upsampled output gradient map. So is this clear? Gradient of loss with respect to filter for a stride greater than 1. How would you do it? You mean to say why are we just putting zeros in them?
Substituting zeros in the middle row
Mhm.
and the middle column.
Yeah, I think that follows from the equation itself. So if you can see, you want to find the gradient of loss with respect to F22, right? So you will have to, you have these 4 terms, right? Gradient of loss with respect to Y00, 0, 1, 1, 0, and 1, 1, right? So this is actually this particular output, this particular output gradient map. Now you are multiplying each term of it with X22, with X24, with X42, and with X44. Now say you want to do this operation by convolution, what would you do? You would just dilate it, multiply element wise on top of this. So you just place this particular map on top of this part, right? So that's a computational trick, like to view it in an easier way. Yeah. Filter. Right. That's specifically for gradient of loss with respect to filter. Okay, so now we'll go on to finding gradient of loss with respect to input. Again, we have the same equation. You're going to find gradient of loss with respect to every input element using the chain rule and then the summation over all outputs. So let's look at the equation. So you want to find the gradient of loss with respect to your first input, x00. So if you look at the equations, x00 is only affecting y00 in this case. So your gradient of loss with respect to x00 is going to be just gradient of loss with respect to y00 multiplied by basically the gradient of y00 with respect to x00. That's going to be just this term f00, right? Similarly, if you see gradient of loss with respect to x01, again, there's only it's only affecting one of the outputs, so you just have one term in that gradient equation. If you look at x02, now When we did the convolution, it was a strided convolution, stride equals to 2. So this was the first one, first output, and the second output was contributed by this particular map. So you can see that x02 is going to contribute to 2 outputs now, y00 and y01. So you can see there are 2 terms in the gradient of loss with respect to x02. Similarly, you can look for x22. So x22 is contributing to all the 4 outputs. So you have 4 terms here. So even this can be viewed as a convolution operation. Slightly difficult to just look at the equation and come up with the strategy, but it can be done by, again, upsampling your output map, upsampling your gradient, loss gradient map, which is this one. And you will also have to pad your gradient map with your S minus 1, that is kernel width minus 1 and kernel height minus 1 number of zeros. So that's the padding that you need to do. Now, why do you do padding? Because we need to do a full convolution, as I think I explained in the stride equals to 1 case. So full convolution essentially means convolution with padding. And you pad with these many zeros in order to go back to the original input size, because you will need the gradient of loss with respect to every single input. So the size of that is going to be equals to the size of the inputs. So you would be convolving this particular map with a flipped filter, as we saw in the stride equals to 1 case as well. So essentially, in order to find a derivative of a gradient of loss with respect to inputs, you will have to dilate or upsample your output gradient map with stride minus 1. You have to pad the output gradient map with kernel width minus 1 and kernel height minus 1. You have to flip the filter horizontally and vertically, and then do the convolution between the 2. So this is how the convolution looks like, and we get back the input size, which is 5 cross 5, right? So again, takeaway for stride greater than 1 BackProp is you can view the gradient of loss with respect to filter, there's a typo here, as a convolution between the input and the upsampled output gradient map. You can view the gradient of loss with respect to input as a convolution between your flipped filter and padded and upsampled output gradient map. So both things will come into picture. Another thing that we would be wanting you to experiment in the homeworks is visualizing the backward of convolution in a different way. The way in which we were visualizing forward of convolution with the question that Aparajit asked about is, what is the relation between the output maps that you get with stride equals to 1 convolution and say stride greater than 1? So you basically drop down a few elements in order to get stride greater than 1 output. So in the back propagation case, you will sort of have to add back the elements. So you will have to do something like upsampling. So that's what we would want you all to experiment in the homeworks as well. So we can visualize the backdrop of stride greater than 1 as upsampling the output gradient map with stride minus 1 rows and columns, and then doing the stride 1 convolution backward, which would just be this. So your gradient of loss with respect to y basically is gradient of loss with respect to output. These are the 2 things, and there's a slight change in the notation, so I'm just making that clear. So this is the upsampled output gradient map. This you just plug into the backward of stride 1 convolution. You should get backward of stride greater than 1 convolution. So this was a small example prepared by one of our TAs. Yeah, come on.
Can you explain how you get the gradient of the loss with respect to y, or the gradient of the loss with respect to the output?
Gradient of loss with respect to y.
Yeah.
So gradient of loss with respect to y is basically same as gradient of loss with respect to O. Is that what you're asking? I'm not sure.
Yeah, but like, how do you get it though? Like, what's the actual?
All right. So okay. So you would in an entire, in an MLP setting, if you will say, not say CNN to begin with. So in an MLP setting, you would have the last layer as your loss calculation, right? So that's going to be the difference between your predicted outputs, whatever the network outputs, and what is your ground truth, right? And from there, you find the derivative of the loss with respect to your predicted outputs. So you have an equation with your ground truth and the output of the network. So first thing is calculating gradient of loss with respect to the output of your network. Now that output of your network that would be generated, that is going to come from a previous layer, right? So then you would find gradient of that output of the network with respect to the inputs to that layer, right? And then you would multiply both of them. That's like the chain rule.
So we just can't calculate it here because we don't have whatever the loss function is.
Yeah, right now, like there are no examples per se, like plugging in the numbers, because this is going to be essentially some number, right? Gradient of loss with respect to y is going to be some number. Yeah. So yeah, this was one example that one of our TAs had prepared, so you can go through it. So this is our filter and its flipped version, and this is convolving with the pattern and the upsampled output gradient map. If you just want to verify the numbers, you can probably zoom in through it in the slides and then check like how it works. So these are some of the references, and that's it. I'll hand over to Amelia. She's going to go through some codes.
All right, okay, so now I will go through sort of like a hands-on tutorial on some of the convolution operations that you can done in PyTorch. But before that, let me just make sure that everyone in Zoom can hear me clearly. Just let me, okay, all right, perfect. Sweet, okay. All right, okay, cool. So yeah, there are, as you can see, like in the table of contents, there are like a bunch of operations that you can do with PyTorch, which is, oh yeah, question.
Is it okay to make it bigger or make the background smaller?
Sure, that's a good point. All right, okay. Yeah, I hope this is clear for people at the back.
You just turn it light.
The light, okay.
We don't collapse. Collapse like.
Oh, okay.
The Helix settings.
And then, oh, that makes sense.
Yes.
Wait. Oops. Wait, does automatically change it? Oh, it's probably because that I have it on dark mode. All right, okay. Now it should be good enough, I think. Let me just quickly refresh this. Oops. Sorry, I think we just have to sort of live with this. Is this okay? All right, perfect, cool. So, cool, yeah, now, yeah, just importing a bunch of stuff at the front, and in the, like at the top of this notebook, you can check out a few of like really useful links. So we have put up the documentation from torch.nn. You can look up various type of convolution 1D, convolution 2D layers. And we have included convolution animations, which is super helpful when you try to do P1 and try to sort of like figure out like what is the input and like how the output is generated. This is also an example of simple CNN model trained on MNIST, which is a digit data set, a really simple one. And to be very honest, like a simple MLP could do like good enough classification on MNIST, but it's like great intro example to play with. Yeah. Sorry? Oh, okay. Is this better now? I'm not sure if I should change anything because I have not done. Okay, cool. All right. Yeah, and last thing is that you can check out the ResNet implementation for Vision. This would be relevant to your part 2 in the upcoming homework too. So just keep an eye out for that and check it out if you're interested. So we will first off start with data format. So images, like when you play with images, which is usually the setting for computer vision when you use CNN, the data format is a little bit different from when you have in homework 1, P2. So as you can see that it usually of 4 dimensions. The first one would be number of samples, which is effectively the batch size. The second will be channels. And as we have introduced before, if you have an RGB image, and you decide to read it as like a channel input, the channels will be 3. If you have grayscale or other things, then the channel may just be 1. The height and width are the height and width effectively of each 2D input. Yeah, so this representation of channels being in front would usually call channels first. Just be really mindful of like what the input parameters order the PyTorch is expecting when you call the functions. Cool. And in addition to 2D data, you can also convolve over 1D data, as we've shown earlier, and also you will encounter that in P1. So 1D data like stock price would have a similar structure, except that it only has 3 dimensions. It will be batch size, number of channels, and time. So in here, number of channels may not necessarily be an RGB, but number of channels may just be how many numbers of features that you may have. Like for example, in homework 1P1, the number of channels here will be 13 because you have 13 features. Cool. And so corresponding to that, your 2D features will usually be structured as out channels, in channels, height, and width. This is corresponding to PyTorch expectation for convolution 2D layers. And similarly, 1D would just be out channels, in channels, and time. Cool. So yeah, different frameworks usually have like a lot of different dimension ordering. So just definitely check out the documentation when you first started using convolution layers. Yes.
I just want to make sure I heard you right. For this data, the channels, number of channels corresponds to the number of features you want to consider?
That is true in 1D. You can interpret that as the number of features that you have for 1D data. However, for 2D, like we talk about the RGB images where you have like 3 channels. So your channels would be 3 in that case.
Like other, in addition to the, like the RGB, if there were other features you wanted to consider, like time data or like other metadata associated with the picture, would that be an additional channel, or are we going to do it totally different?
I think it will be different. Like I don't think you can do like a 2D convolution then. I think you probably need like another dimension to keep track of that. It depends on like what you want to do. If you want to do like for example video frame by frame, then it's good if you have like 2D because you're just looking at one frame. But if you also want to consider multiple frames, then you probably need another dimension to keep track of that. Cool. All right, yeah, and so here is just some random random to generate some sample images and sample signal. So as we can see here, 1 is the batch size, meaning we only have 1 single image. 3 is that we want to sort of create like an RGB image. Therefore, we put 3. And 32 by 32 just mean the width and height. Yeah, and it's expected that it should come out as 1, 3, 32, 33. And the second is input signal. So it's really similar. So we have like 1 signal, and the signal has 40 dimensions. So the number of channels here is 40, and 100 just means that you have 100 time steps to consider. Cool. So that's that. And yeah, here is like a quick example of how you can invoke the Torch Conv2D layers. So you can check out this link for documentation. And also just oops, there's a typo here. It should be output width instead of output width. But like essentially you can compute the output width and output height according to this formula here, which is the same as we presented at the former slides. So as you can see here, what you can do is that you can first create the layers. So you would just call torch dot and then come to the, you pass in the in channels because that in our input image, the channel is 3, therefore you just pass in 3. Out channels we pass in 20. So this is out channel effectively means that how many channels that your output will have, which equal to the, yes. Oh, sure, okay. Which is equivalent to the number of kernels that you will have. So that we would just put 20 there. Kernel size is the width and height of your fuser. So it would be 5 by 5. And straight equals to 1 just means that we are not skipping anything. We're just like doing normal convolution. And we pad, do the padding. Cool, so that is the first convolution layers that you have seen in this class. And then we just pass the input image through layer C to D. And then after that, we get the output. And when we print out the size, we can see that now the batch size is U1 because we only have one image, obviously. However, the out channels now become 20 because the out channels is 20 and we have some kernel size. And 32 and 32 stays the same. However, they stays the same does not mean like there is no changing in the elements. It just so happens that the output width after you calculate through this formula is 32 by 32. Cool. All right, if we don't have questions, I will keep going. Yeah, just as we mentioned before, like padding is sort of important, and padding really impacts the width and height of your desired output. So here I have created a bunch of examples. When you start with an input of 1, 3, 32, 32, and we just have a bunch of almost the same convolution to the layers. The only difference is how much they pad. So you can pad, does not pad, you can pad 1, 2, 3, and you can also pass in the tuple to specify how much padding you want on each side. And as you can see that the end result differs because you pad differently. Cool, yeah. And the next thing is that when you want a more, I guess, like a refined padding, you can use the replication pad 2D layers in PyTorch. I think there are a bunch of other padding layers in PyTorch as well. So you can definitely check that out if you're interested in different types of padding. But this is not extremely important. You can read it by yourself. Yeah, this is just repeating what we just said. A bunch of common padding layers that you can look into. Cool. Next, we will talk about upsampling and downsampling. So there are a few ways that you can do upsampling. The first way is that you just upsample by just a normal convolution and then do something called a pixel shuffle operation. So pixel shuffle is not the central point of this tutorial, and it could be like a technique that you may be interested in, but like essentially you can read the original paper that proposed this pixel shuffle operation. Essentially, it produces a high resolution image from a single low resolution one by like reorganizing the shapes of the channels. And so therefore that effectively is a type of upsampling. And the second type of upsampling that you will need to complete in homework 2.1 is something called transpose convolution that we will touch upon in later lectures. And also you can look it up in the homework write-up if you're interested in the details. Yeah, cool. So like this is a quick example of how you will just do the first half of upsampling. So you can first pass through your image features through a convolution of layers. And then PyTorch actually implement the pixel shuffle for you. So as you can see that it's effectively upsampling by double. And you can also just use the unending upsampling layer, which is just another layer type that you can use for upsampling in PyTorch. And PyTorch also supports transpose convolution, so you can directly use that layer if you want to see like how that operates in PyTorch. Downsampling is like on the other hand a different operation. So you can think of it as sort of an inverse operation, though not exactly, depending on how you technically want to implement it. So you can either do max pool and average pool, or you can just simply do a straight convolution, meaning that you have straight equals to 2. So in the homework, you will be implementing convolutional layer with straight equals to 1, and then call downsampling or upsampling depending on your intention, and that will be equivalent to when you do convolution with straight greater than 1. Cool. So that's that. And Yeah, I think that this is just what we have talked about. There are a bunch of layers that you can use, such as conv, 2D, and polling layers. Convolutional function, it's a function. It's like not torch.nn layers, it's torch.nn functional. And you can also play with this if you're interested. But like I would say this is not extremely relevant to the homework, so you can check it out on your own. Normalization and dropout would be important for your homework to part 2. So you just need to be mindful of sort of including that when you're developing your model. So it's really similar to how you will use batch norm and activation and dropout in MLP. You just stack each layers all together and then just get the result as one convolution like block. You can think of it. Cool. So that is like all the basics. Now I will talk through like a really simple example of how you can build a convolutional layer network and how you just do training really similar to what you did in homework 1 part 2. And here is an image. So like, because we like in homework 2 part 2, we will probably give you images in JPG format. So you can actually just directly download some image and just examine to see like what the image is about. And on the other hand, you can also just watch like see how that looks like in Python. So you can just do SKI image and just read it and use matplotlib to plot the image out. So yeah, so this is just 2 images. Like be mindful of like the path setting is such that we have a top level directory and we have each person and the images of that person as sub directories. Yes, question.
For homework 2 part 1, are we implementing our own background 2D and dropout 2D, or we just need to know that it's a good idea for the part 2?
I don't think you need to implement batch norm 2D and dropout 2D. Yeah, right. You only need to worry about mostly convolution and flow stuff. Yeah, cool. But oh yeah, but like this is important for part 2. So right, so this is that. And then when you read in data, like remember how in part 2 of homework 1, you are writing your own data set class. However, PyTorch provide us really a really convenient dataset.image folder for you to load image data specifically, so that you will only need to pass in the directory to your root directory, which is your top level directory, and then also pass in a bunch of transforms. So these transformations, you can think of them as like data augmentation. They effectively just apply a bunch of transformation of your choice to the images. So you can just check with like random resize prop or random horizontal flip. There are a ton of different data transformation that you can do. And in order to figure out which type of data transformation you may need, it's a good idea to examine the images first. And after you get the data set from image folder, you just pass into data loader, just like you did in part 2 of homework 1. And after that, everything else should seem really similar and real familiar, to be honest. You just loop through each batch from the data set loader and just read it through and pass it to your model. Cool. So here is a sample basic CNN model. Note that this is not like your starter notebook or anything. This is just an example of how you may structure a CNN model code. So in the init, we are defining a few of the layers sequentially. We started with conv2d in channels 3 because we have RGB. And then we just have a random out channels and kernel. Then we have activation, polling, and then another convolution. Note that you need to include a flatten layer after your last convolutional layer, because when you pass into the fully connected linear layers, they are expecting a 1D array, like they're not expecting a 2D or 3D input. And so therefore you need to effectively flatten the features that you extracted with your convolution module and let the fully connected layers to do the classification for you. So just be mindful of that. Cool, yeah, and everything else is the same. In a for function, you just pass your output through each layer and then get the effective final result. Yeah, so as you can see here, this would be the result of calling basically in the module, and this would be exactly what you will get. And yeah, here we also included a few snips of code if you have not played with saving and loading your models. So you can just take a look at this and just load and save your model, your checkpoints effectively when you do training. Yes, question.
Scroll up.
Sure.
Do I?
Oh, okay. Yeah, so you can like again, like the number of fully connected layers really depends on your design choice of your model architecture. You can have maybe 2 linear layers or 3. If you feel like 1 linear layer is not doing a good enough job. But you can definitely start with just playing with 1 linear layer and see how it does, and then maybe add more to like do a better classification job, essentially. Cool. Yes.
Those are just 3 linear layers, no activations, no dropout, no back. Isn't that the same thing? As
Exactly.
one linear layer?
Yeah, so we actually do ReLU. Like we cannot like define and then the ReLU in the init. That's why it does not show up. However, in the forward, if you take a look at the result of FC1 and FC2, we are passing it through ReLU. So yeah, we have nonlinear activations in between. Yeah, this is really important. If you only have linear layers without activation, without nonlinear activations, you're effectively only playing with one big gigantic linear layer, which is not extremely helpful for your purpose.
Okay, so you're initializing the size of the layers in the init function, but then you're doing activations.
Yep.
So it ends up looking a little different than what like the default, like the target code looks like in homework 1, but it accomplishes.
Yes, yeah, it's effectively the same thing. It's just that, yeah, it's just that we do not define that explicitly in it. Cool. All right, yeah, and then the training loop. The training loop should look really familiar up to now. So as you can see that we just have like number of epochs, and then you're enumerating through the data loader and just get the features and labels. You pass it to the device, and then you just get the model output, and then you just do like a loss and then just backprop the loss. Yeah, so effectively these are like this should be really familiar to you by now, but if you have not played with like saving and loading your model, just check this code out to see how you can do that. Yeah, cool. I think that is all of the main materials, and at the end there are like 2 short sections that cover how you can visualize your CNN features. So yeah, so this is what so like basically you can pass your inputs through a convolution layer, and you can visualize how each feature look like as the output of that layer. And we have put up, yeah, like basically 2 examples here, and you can examine that to determine how your convolution is working. And the last thing that we have included here is an example of using pre-trained models directly from PyTorch. So in here we are using UDG16, and yeah, you can just basically load UDG16 and then just do maybe like the last classifier on top of that, and just get and just basically pass your inputs through UDG16 to get the output. Similarly, you can also do ResNet, I think 1834, and here we use 152, which is a relatively large model. But yeah, PyTorch supports a variety of different pre-trained models for you to play with if you're interested. Yes, question.
So are we allowed to use between
So okay, so I don't think you can just directly call. You probably need to implement it yourself. Yeah, but you need to refer to the original paper, like to get the original architecture, or we will also provide more guidance on it in the bootcamp and in the Star notebook. Cool. Yeah, all right, I think that's all.